Thank you, Florin, for the introduction. Um, so I want to be talking a bit about perfect hash. Perfect hash is a library that's on PyPI now that I actually only uploaded to PyPI 3 years ago, and the name wasn't taken yet, surprisingly. Even though I created this library, it was one of the first projects I created in 2007 or 8, I believe. It was a very long time ago, but yeah, I didn't think much about it until I saw on Hacker News a thread about this library, and other people were using it and had questions. So when I first created it, I just made a little tarball and put it on my webpage. It wasn't on GitHub, it wasn't on PyPI. I'm surprised people even found it, but it was useful enough for some people, so they found it. And now it's also on GitHub and on PyPI, and has more documentation as well. So what does this library called Perfect Hash do? I'm sure most people are familiar with hashing, at least to some degree. Hashing is the process of like taking an object, let's say for simplicity, like a string object or some bytes, and turning that into an integer, usually a 32 or 64-bit integer. And there's different types of hashing and different applications of hashing. There's cryptographic hashing, and the point there is to have a hash function where the output, the hash value, always looks as random as possible, where you cannot infer the input from the output of your cryptographic hash functions. And those are used in blockchains and cryptocurrencies and things like that, SHA-256, things like that. Python has a built-in hash function that is used for the implementation of the dictionary hash table. And Python's hash function is actually a lot simpler. It's not a cryptographic hash function at all, which actually isn't necessary if you just use it for a hash, for a hash table, for a lookup table. And in addition to that, Python uses what is called closed hashing, which means you have a single hash table with all your slots of information, and the information is basically the key and the value of your dictionary. And then, so let's say a key comes in and you want to look that up, want to see if that's already in the dictionary, and if yes, you want to return the value. Python first creates, calculates the hash function. And well, this hash function is also usually like 64 bits on 64-bit machines, but that is like truncated to the last few bits, depending how big your hash table currently is. And let's say you have a hash table with 32 entries or something like that, then you will get a number, let's say 27, and you look that up. And if that slot is empty, then you know the key is not part of the hash table. But if it's not empty, you would have to compare the actual key to make sure. And if it's not identical, then what is done in closed hashing is that you move to another slot. The most simple method to do that would actually be just to try the next one. Like if 27 is already occupied, you try 28. If that's occupied, you try 29, and so on. Python actually uses something more sophisticated there, but yeah, that is more an overview of how the hash table in Python works. So there we have basically a universal hash function, and what I just mentioned were these so-called hash collisions. Well, actually, yeah, because if you didn't have hash collisions, you didn't have to probe for other empty slots, or you wouldn't have to check if the key is actually correct. So usually these hash collisions can happen, and Python uses closed hashing to resolve them. There's also something called open hashing, which is actually usually implemented with a linked list. If you have a hash collision, all entries in that slot are just added to a linked list. Now, what is perfect hashing? In perfect hashing, there are no hash collisions, but that's actually only possible because we construct the hash function from a given set of keys. So you have a very special hash function that, given only the keys that you're interested in, will be perfect. Perfect is just means collision free. And yeah, so I will talk about perfect hashing here. Yeah.
Am I understanding this right, that in perfect hashing, you adapt the hash function to ensure there's no collisions?
Yeah.
Okay.
Yeah, exactly. And so I'll be talking about perfect hashing, and the package, perfect hash package I created, actually uses minimal perfect hashing, where there are also no empty slots. But yeah, I mean, that's actually easy to achieve. Once you have a perfect hash function, any perfect hash function, you could simply in an array map to a reduced number of slots that are in consecutive order. So how would you go about creating such a perfect hash function? One easy
Give them an example of
way,
hash function. So
but one
how
not very
how
efficient way to do that would be to just take a regular hash function and add some like random noise or some what is called salt to it. You just have this extra salt string that you randomly generate. And let's say you have 100 keys. You calculate the hash with this random salt of these 100 keys and look at all their all the hash values. And well, of course, the hash values themselves, it's unlikely that there will be a collision because that's usually 64-bit integers. But now let's say these 100 keys you want to map onto, say, 128 slots, then you will almost certainly have a collision. So you would have to try and modify this salt, for a very long time until you have no collisions anymore. I mean, that it's feasible to do that for very small sets of keys, maybe, I don't know, up to 10 or so, but after that it becomes impractical. So what is perfect hash doing here in this case? Perfect hash, this library, is it actually, I wrote, here, I wrote this also when I created this a very long time ago. So perfect hash uses an algorithm by which first you create two hash functions, two random hash functions with two different types of salt. And then you, from all the given keys, you create a graph. And if that graph is acyclic, which means it doesn't have any loops, then you connect, like for each value corresponds to an edge in the graph. And you can assign edge values such that once all these vertex numbers are assigned, that then you can easily calculate very quickly the actual perfect hash value. And this is possible because it's acyclic. You don't have any loops, and you basically traverse each of these, like these subtrees.
Can you zoom in a little bit? I can't.
Oh, I don't know if I can make it bigger.
Oh, sorry.
But I don't want to.
That's okay. I'm sorry.
This I just want to give an overview of how this is done and now more talk about the practical application. So here's a graph with 50 created for 50 keys, a perfect hash function with 50 keys, and yeah, the number of nodes is slightly bigger. It's like 66. And the way the algorithm works is it starts with a small number and then tries to find this acyclic graph. And if it can't do that within like 50 or 100 trials, then it increases the number of nodes, the number of vertices. And well, here I've done this for, I think it was 100,000. And this was done in 2008. So what does this actually look like? So you have an input, which can be like a text file with keys. Here's this list of keys, in this case, animal names. And then you call perfect hash and give it this list of keys. And it generates code. By default, it just generates this piece of Python code, which is the implementation of the perfect hash function. So here you can see a hash function, hash underscore f, and it's it just sums over each of the characters. Each of the character times like the ASCII value of this hash here. And yeah, then these two hash functions are combined. And yeah, that gives you the perfect hash function. And then this program here also that it generates also has the keys themselves in it and a test, making sure that each key actually maps to the correct position. And the perfect hash library has also some ways to fill like templates. So like this is only the default, but you can also construct your own hash functions. You can also construct a code template, and I'll show that in a bit. So yeah, maybe I'll just show it now. I know that might be too small. There's no reason to have it this small. Oh, no. Okay. So I say perfect hash in this animals txt. This creates a Python program. Well, I guess I can just pipe this to Python. Yeah, and it doesn't give any errors, or I can just pipe this to a file, t.py. This is my file. And then I can run this code. And yeah, that's nice, but I mean, you can already do that with Python. Let me show you an example. Here's an example where I create in this make file, I create here random keys. I have this little Python script here, which I can tell to create 50 random keys. And then once I have these keys, I can tell perfect hash to fill in this code template. Let's look at this. Actually, yeah. So this is my code template. Here's where this array G goes. Here's some constant number of keys, vertices, length of the salt string, and a character array of the actual keys themselves. And here I built an index function, and it consists of these two hash functions to find the index. But once it finds an index, it also needs to actually do this final comparison, because you can give this minimal perfect hash function, you can give it any key and it will return something. So you need to check at the end whether the key is actually correct. Yeah, but that's all you need. And then I have a small test here where I test different, well, I test first these different chunk keys, and then I test actually the index of all the real keys. Compile this. Now it generated these hash functions. Now I can look at my main function, my main program. Nicer Emacs. So here you see all the different random keys for testing. Here you see the hash function, the two hash functions with their salt. And yeah, and now we can run this. Yeah. So the nice thing is now you have this small pure C program which implements this perfect hash, and it's not very long, and it doesn't depend on some large library to do that. So maybe I should talk a bit about the application of these perfect hash functions. You wouldn't normally want to use them in Python, because Python has a dictionary that's already built in. It might be that in some cases this is more memory efficient or faster to use a perfect hash function, but effort, in particular, since you need basically a frozen dictionary. But where these minimal hash functions become important is when you have a static set of keywords that you want to map to indices. I had one comment or an issue on GitHub. Someone was working on I think it was a Fortran or some other language compiler, and he used these minimal hash functions for the some keywords. Yeah, I forgot exactly, or some keys in a database table or something like that. And yeah, then you can, using this, create very efficient small programs to find those indices to those keys. I would imagine this can also be very useful when you do like programming in very small, like embedded devices, things like that, because like all the hard work is done beforehand at compile time here when that minimal perfect hash function is calculated. But yeah, once you have it, then this program is very simple and very fast. So that basically concludes my talk. Are there any questions?
Curious about the functions it was generating. Can you go back to the Python?
Python. This one?
Yeah, is that like a typical result that it generates for the hash function? It's like it always finds like it always can do the job with like 2 salts and combining them like that. Is it ever gonna like have to do like add 3?
No, it always uses
Ilan, can you,
2 hash functions. That
for
it
the
combines.
recording,
I mean, this has to do with this algorithm. It takes each key and each of these hash functions connects basically 2 vertices in this graph, which has to be acyclic. It's always 2, but I read that there are other more sophisticated and like this is, I mean, I didn't test this for extremely large sets of keys, or only up to a few 100,000 maybe. But I read that if you go to like billions of keys, there are actually more efficient ways to creating such a perfect hash function with 3 random hash functions and not 2.
And like on my ways, it's always that same hash function. That's always the same regardless of.
Yeah, this is always the same here. This one. It's just the salt here. This T that changes. But you can actually, I have an example folder here, and you could actually construct different types of hash functions and do some experimentation here as well. So here I have this program called Python hash. And here what I did, I just used Python's hash function itself with some salt to create the perfect hash function. that's also possible. I mean, this is more like an experiment because, like, I mean, what's the point? Once you're in Python and have access to the Python hash function and all that, at that time you might just as well just use the Python dictionary.
Yeah, I was kind of curious about the acyclic graphs. How did you generate those?
Yeah, this was here somewhere. On this page it describes how these acyclic graphs get created. So I choose two salts, then I have two random hash functions, and I test each key. Like in this example, here has the abbreviation for all 50 states as the key, like AL for Alabama, CO, Colorado, and so on. And now here, for example, let me see. Here's Texas. Texas has a hash value of 42 because we want in this minimal perfect hash function we want this to be the index. And using this input tx, we get from the hash functions these two values, 50 and 64, which are the numbers of these two vertices. And then these vertices get assigned these numbers that add up to the desired perfect hash value. And while you construct this, you can easily do that because there's no loops in the graph. And here's the code that does that. Here's the code. You have a method to connect two vertices with an edge value. And then here's the actual method that assigns all the vertex values. It's a bit tricky, but not too bad.
Yeah, so the way I understand it is the vertices are the hash, the generated hash values, and then the edges are the actual data that you're trying to store.
Yeah, the edges correspond to the actual keys. Each key, because each key creates two numbers, two vertices, and two vertices have an edge. Yeah.
Have you been surprised by anything that people have been using this for? Like, what's something that you've been surprised by, where people have been
Well,
or
not too many.
Just the use case in general.
Not too many people have used it. I mean, it has few stars, some issues, but I found it interesting. This one issue was most insightful to me, where Let me see. Maybe it was even a pull request. I'm not sure. No, there are no pull requests. Which one? Yeah. Yeah, here this guy. Be Riot. He was using this for some type of, I don't know, trading platform database code. I don't know, because here, this is actually all the keys he has, like has trading status, has bit, has off-book trade, all these things.
Okay, so this is to generate like very fast, essentially lookup tables.
Mm-hmm.
Okay.
Yeah. Very fast and very memory efficient.
Yeah. Sure.
I'm confused, though, like if he was actually doing a trading thing, we would probably like somehow convert the numbers so it doesn't have to like feed all the characters.
Yeah, if you're talking to some other system that only takes
Mhm.
a number, then you need to, and you want to assign like a semantically meaningful
Yeah.
name to that. This is probably the way to go.
I mean, you could use that in any, like in a programming language, like all the keywords in Python, you could assign numbers to. You could do that using minimal perfect hash functions.
Seems like it'd be useful to speed up like a zip library or something. Where they have fixed dictionary sizes and stuff.
Mm-hmm.
Just fun.
All right. Any other questions? Oh, there's chat questions. I haven't looked at those at all.
A lot of chat.
Don't even know how to do that.
Probably more like comments.
Mhm.
Questions there.
Oh, here, chat. Mhm. David Hirsch is asking something. Mhm. Yeah, cryptographic hash function. Okay.
I was familiarizing myself with the terms. Thank you.
No questions there. Well, thanks so much. It was awesome talk.